we could argue that natural selection would probably select for traits that increase dispersal ability if the likelihood of reaching a new patch, right, is pretty high. On the other hand, natural selection might select against individuals that disperse if there are no good habitats to disperse to. So one of the classic examples that's given for dispersal ability and all this is islands. If you look at species that are on islands that also occur on the mainland, over evolutionary time, and I'm talking about species that haven't been brought there by humans, these are naturally occurring in both places. If you look at species on islands that have been there over evolutionary time, they often don't have any dispersal ability because natural selection is selecting against individuals that have traits that allow them to disperse, because the likelihood of being able to get over to this wonderful patch, it's just too far away. And therefore, any individual that attempts to disperse, fitness goes to zero. So you often find on islands traits like flightless birds, right? The flightless bird is a pretty common thing to find on an island, right? Or reduced wings in insects. This idea of the likelihood of getting here is pretty much zero, and therefore any individuals that try it, they're selected against. The ones that are selected for are the ones that don't have those traits. Whereas in other habitat types, you get selection for the dispersal ability because the likelihood of finding a new patch is actually pretty good. Okay? All right, I put the link in here so that a few of you might try to read through this. I see, based on the language and the answers, I see that you did. It's actually a pretty classic paper. As an aside, Phil Levin is a fish biologist. He's currently with NOAA in the Pacific Northwest. He was a fellow grad student when I was in graduate school at the University of New Hampshire. And Don Levin, his father, is a very famous plant evolutionary ecologist who retired from the University of Texas at Austin, and I took a couple classes from him when I was at the University of Texas. Okay, in any event, their paper is really good. The Levins argue that the number of species today should be equal to the number of species in the future, even with the world currently in a mass extinction period. Many people have argued that we're currently in a mass extinction period due to human intervention. We kill a lot of species. We drive them to extinction, like dodo birds or passenger pigeons, but we also drive a lot of species to really low numbers, like cod in the Gulf of Maine or redfish in the Gulf of Mexico, because we overfish, we overhunt, we do a lot of that, but we also introduce other species to other areas like dogs or cats that then reduce other species numbers and cause extinction. So we have big effects, and if you're kind of keeping track of that stuff, we are in a period of loss of species. All right, they put their argument as we would expect the total number of species to ultimately recover from the current mass extinction, even if people continue to meddle with the environment on a global scale. And how is this possible? Well, you want to go to the broken stick model. The broken stick model suggests that any niche axis, doesn't matter which one you want to talk about, but any niche axis here is going to be occupied by a finite number of species. And the number of species on this axis is defined by the length of the axis. Each species needs X amount of space on this axis. Now, if humans come along and start removing species, we're effectively removing those species from niche axes. So let's say that we come along and we remove species 2 and 3, but 1 and 4 are still there. When they say ultimately recover, they're talking about a very long-term process where the niche breadth will increase for species 1 through ecological release. And species 4 would do the same thing through ecological release. And then following that, we would get some differentiation between the two ends of this niche axis for this species, and we would get the original 4 number, the number 4 species that we started out with, but unlike the original niche axis, which had 4 species, we now have a niche axis with 4 species on it, but these are 2 new species, and furthermore, this one is very closely related to that one because it evolved from that one. This one is very close to species 1 because it evolved from species 1. Okay? So the first part of the answer is, yeah, ecological release, sympatric speciation is predicted by the broken stick model. Any niche axis that you talk about where we've got these species lined up like this provides an opportunity for this process. The second part of the question, just go up, they argue that the number of families probably provides a better measure of the diversity of characteristics and evolutionary potential than does the species. Okay, their argument is that given the process you discussed in question 1, this process, ecological release, sympatric speciation, the world would look very different if these processes began with fewer families. So if humans start removing species, and ultimately we remove the families because we remove so many of those species within the family, then the number of species will recover, but the recovered species represents a smaller group of families than we started with, which they argue is a loss of genetic variation in much the same way that Darwin's finches on the island diversified through ecological release and sympatric speciation, that you had finches that had the same ecological niche as a woodpecker. That is, it had a beak that was used to beat into wood and pull out insects, but it still looks like a finch. Genetically, it's still a finch. It's not a woodpecker. The woodpecker and the finch are very different genetically, whereas 2 finches that derived from the original finch would be very similar to each other because they belong to the same family. So the argument is, yes, we expect species to replace other species as they're lost from their niches, but we can't just say, well, it doesn't matter what we do because I could kill off as many species as I want because other species will just replace them over evolutionary time. Well, that's certainly true, but their argument is that even though that's true, you are losing something, and what you're losing is this genetic variability that in the future may come in handy for all sorts of reasons. All right, following data collected for a graminoid. All right, so survivorship is 1. This would be 0.9, 0.8, 0.7, 0.1, and 0.01, I think. 350 out of, yeah, it's 0.7. And then we would take Lx times Vx. That's a 0. It's 0.09. Yeah, let me pull out I have a spreadsheet here too we can play with. So this equals 0.9 times 0.1. That's 0.09, and then 0.8 times 0.2. It's 0.16. And then This would be 0.7, 0.3, and no births occur here. That would be 0, 0.0, and that's the LX, BX. So if we take 0.7, 0.3, let's get the sum here, 1.25. This is the sum of the LX, BX equals R sub 0 equals 1.25. So many of you use this information to say, hey, we already know the population is increasing because the net replacement rate is 1.25. Okay, then we can fill in the X, LX, BX. So this would be 0, 0.09, 0.32, 2.1, 0.3 times, 21, 4 times the 1.2, and that's a 0. And then if we sum up the X, LX, BX, that's 0.09 plus 0.32 plus 2.1 plus 1.2, 3.71. Okay. All right. Then we could do the sum of the X, LX, BX divided by that. Shouldn't have gotten rid of my calculator yet. Pull up my spreadsheet. And just say this equals 3.71 divided by 1.25, 2.97. That's the mean generation time, and then we would do the gth root of R sub 0 equals 2.97th root of 1.25. Yes, I know I'm rounding before I should, but I'm not doing this on an exam. I'm doing it to show you how to do the math. So this would equal 1.25 raised to the 1 divided by 3.7, no, 2.97. 1.078. And that's the population growth rate. Okay. All right, so what type of survivorship curve does the population show? I put this in here because most survivorship curves are done with log transforming the size of the population. So you could either do this column, and you see there's this huge drop off. So it kind of goes like this, right? If you plotted it, it would go like that. That feels to me like a type 1 survivorship curve. A few of you argued that it looked kind of like a 1 and a 2. I'm okay with that too, as long as you backed it up with some language. And then what does this imply about their life history? It implies that there's very good survivorship early on in life, and that as you get older, your survivorship begins to drop, very similar to humans, as opposed to an organism that has horrible survivorship early on, but once they get to be a certain age, i.e. a certain size, their survivorship is great. What age accounts for the most reproductive output? The total number of offspring produced. Well, age 0 produces 0 offspring. Age 1 produces 45. Age 2 produces 80. Age 3 produces 350. Age 4 produces 150. So age class 3 produces the most offspring because they produce 350. What is the population's intrinsic rate of increase? That's my bad. I should have put population growth rate. The intrinsic rate of increase is R. Many of you from lab were doing the log transformations to get from R to lambda. That's fine. I don't think anybody got points off for this unless they were really off base. But yeah, the intrinsic rate of increase you could report as a lambda value, the rate, or you could log transform it to get the intrinsic rate of increase. But in any event, the population is growing because lambda is greater than 1. You could also say that the population is growing because the net replacement rate is greater than 1. Okay? Overall, the exams were very good, just like they were very good on the first exam you guys did. We should be getting close to me distributing the next exam before the final exam. I will probably distribute that third exam a little early because I don't want to back everything up till the end of the semester and put you guys in a pinch. That way you can complete exam 3, still deal with your other classes, and then deal with the ecology final kind of at the same time. I'll probably distribute that early too. Okay? All right, so what I'm going to do is go ahead and break things here, reconfigure so that we've got our PowerPoint back as well as the screen, and I'll see you on the other side.